Okay, so welcome to Math Stat 341. And what I want to do today is I want to talk about applications. So we're going to talk about a game that I created with my children years ago. That game is going to involve logarithms. The lecture on Monday will be on the method of least squares, which will also involve logarithms. So what I thought I would do is spend a couple of minutes in the beginning quickly describing what are logarithms, why do we care about them? This is a talk you should have had with one of your teachers years ago. I don't know, maybe it's like other subjects and teachers feel a little bit uncomfortable talking about logarithms. And so this has just not made it into your conversations in the past. And I will try to fix that now and just have a little bit of a conversation on logarithms. So why do we care about logarithms? Well, one of the reasons is that they allow us to discuss objects that span numerous orders of magnitude simultaneously. And the other is they linearize a lot of nonlinear functions. And we're going to see a lot of applications of that today and on Monday. So for example, for this image, it always is a question of how good is the screen? Has it been cleared and cleaned recently? This is to scale. This is the sun. This is the earth. And there's the moon over there. How do you talk about things that span so many orders of magnitude? And of course, this doesn't even begin to go into, well, what if we looked at the size of the solar system or the size of the galaxy or the size of our cluster of galaxies? How do you talk about all of this? And of course, you could go all the way down to the atomic scale. So just briefly, what is a logarithm? So if x equals b to the y, then the log of x base b is equal to y. So we often use base 10. Why do we use base 10? Yeah, exactly. We have 10 fingers. What is the natural base to use? Well, if I'm saying the natural, one possibility is to say base e, because for calculus, the derivative of e to the x is e to the x. So calculus is easiest in base e. Computers love base 2, on, off, yes, no. These are very easy things to build. This is one of the great advances of the 20th century, was this idea of doing binary operations and building machines like this. So, just to have a couple of examples, if 100 is 10 squared, then we'd say the log of 100 base 10 equals 2. So I'm not going to go through the rest. I'm assuming you've seen how to do computations like this. So here's a beautiful scale that just shows you exactly what I was talking about a moment ago, going from the distance of nuclear particles all the way up to the distance to the furthest photographed galaxy. And this is about 40 orders of magnitude. And it's all fitting on one slide. And I'm not even using expanded margins. Okay, it's amazing to be able to talk about things that are this different. Yet when we look at it on a logarithmic scale, it's differing by 40. That's equivalent, if you want to think about things in Fahrenheit, maybe between the daily highs and lows this time of year. So amazing that logarithms allow us to talk about stuff like this. Just some examples of where you've maybe seen logarithms before. So this is earthquake frequency and destructive power. And just, keeping track of just, how many are they and how destructive are they? Can anybody give me any scales they've seen from science that are logarithmic? So decibels is a logarithmic scale. What else? There's two others that you have seen. Yes.
What's that P scale one?
I've led a nice life, so I'm not really that familiar with pain scales. If you're from San Francisco or California, you might know earthquakes, the Richter scale. And then chemistry, acids and bases, pH scale. So noise level is decibels. And then, this is just showing you just how different because if you say, oh, this is only 10 decibels louder, that doesn't sound that bad, but it's actually an entire order of magnitude. The pH scale going from acids to bases. Did you figure out what the pain was? No. All right. So just a couple of plots of what the exponential and the logarithmic functions look like. So here's plotting, three different exponentials, 2 to the x, e to the x, and 10 to the x, as well as their logarithms. You never have, when you exponentiate, you never have a negative number. You can never take a logarithm of a negative number. All right, we talked about how these allow us to discuss things across many orders of magnitude. What I want to focus on now is if I take this plot, like the 100 most populous cities, and I do a log-log plot of it, it now looks like a straight line. One of the big ideas in calculus is you reduce any complicated function locally to a straight line. This is Taylor series. By doing a log-log change of variable, we can often convert nonlinear relationships to linear relationships. So did anybody talk to you about this when you were learning logarithms as to why we care so much? Okay. So again, they linearize many nonlinear functions. If I look at these functions, x to the 1/4, 1/2, x squared, and x to the 4th, I can see x to the 4th. I can just barely see a little bit of maybe x squared, and the other ones are completely dwarfed. But if I look at it and do like a log-log plot, all of a sudden I can now start seeing all of these functions. All right, so you should be comfortable with a lot of the properties of exponents and logarithms. Just because it's been a while, if I have b to the m times b to the n, it's b to the m plus n, you just add the exponents. And there's a nice interpretation. I have m copies of b followed by n copies of b. I have m plus n copies. This all makes sense, at least if m and n are integers. And then in a real analysis class, you justify extending this. Similarly, if I have b to the m raised to the n, that's b to the m times n. Okay. I should have brought down my slide rules. I actually do have a bunch of them. Beautiful, beautiful device to allow you to do a lot of these computations. We have the following basic theorems of logarithms. The log of x to a power is the power times the log of x. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And the log of x base b is the log of x base c over the log of b base c, which means we only need to understand logarithms in one base. We talked a little bit about this with the central limit theorem about why this is so important. I'm going to just quickly do some of the proofs. I'll leave the rest on the slides. If you want to see the details, you can just go there or ask me. We did the change of base formula. Let's do the, so this is this the log of the product? Okay, let's do the log of a product is the sum of the logs. So the log of x1 base b equals y1, the log of x2 base b is y2, means x1 is b to the y1 and x2 is b to the y2. We want to look at the log of x1 times x2. Well, it seems pretty natural to say, well, why don't I just multiply x1 and x2? This really is a follow your nose proof. And so if we multiply x1 and x2, we have b to the y1 and b to the y2. Oh, well, we can just add the exponents. And now by the definition of logarithm, the log of this number is just how many powers of b do I need to get that number? Well, it's just going to be y1 plus y2. And then we just substitute for what y1 and y2 are, and we have the proof. So if we wanted to then do the change of base formula, we did that one before, so I'm not going to really go through the details of that. I'll just leave it in the slides. This is the one that in some sense that's the most important for what we're doing in probability, because it really drives home this idea of standardization, that you only need to understand things in one base and then you convert this. My father used to work in high tech many, many decades ago, and all the different companies had their own computer languages. And we were talking about computer languages before class today. And you would sometimes have a trouble where you would have to speak to somebody's computer and your computer and their computer didn't speak the same language. But everybody had to speak IBM because IBM was such a powerful force in the market. So what you would do is you would have your computer talk in IBM and the other person would talk in IBM back. It's not quite as good as the tourist who was visiting Japan, couldn't communicate with one of the locals there until he found out that they were both Star Trek geeks and started speaking Klingon. But you need to find a common way to communicate. You want to find a way to compare things. You want to compare apples and apples. This is a common expression. And so if you standardize, you now have something that has mean 0, variance 1, much easier to compare. Just a little, simple code to look at, the factorial function, just how rapidly it grows. We talked about this with Stirling's formula. And, if we try to plot it, it just, shoots off so incredibly fast. When we're looking at, and here's, 10 to the 295, and just shooting up extremely rapidly. But if I do a semi-log plot or even a log-log plot, I can start to see a little bit more of its growth rate. Now, notice it's not linear in a log-log plot. We have n to the n, e to the minus n. N to the n is growing very, very rapidly. That's growing, even when you take a logarithm, it's growing like n log n. All right. So now that we've quickly reviewed logarithms, I want to turn to an application. So this is going to be the first of 2 days on applications of logarithms. And so cultural extra credit to anyone who can get the Peter Sellers movie that inspired the title of this. From Eminem's to Mathematics or Dr. Strangelove, yes. And if you want, I'll give you some money to buy a can of Coke later. If you get the reference, I'll give you some money to buy a can of Coke later so you don't have to smash open the machine. Right, outstanding movie, Dr. Strangelove, or How I Learned to Quit Worrying and Love the Bomb. So I gave this talk to a conference on science teachers, math teachers in Massachusetts many years ago. And this was at the 110th anniversary of the association. And I was talking a little bit about what are the issues in the future of teaching, in the future of how we're going to have the kids learn and do mathematics. The world is changing immensely quickly. The amount of computational power we have at our disposal now is just magnitudes more than what it was when you were young, which is orders of magnitude more than what it was when I was young. And when you go back to my father, who learned and actually had slide rules, it's very different. What skills are we teaching, and what skills should we be teaching? Does it make sense to memorize everything? Well, in the 21st century, you have so much easy access to information. If you have to use a calculator to figure out what is 3 times 4, okay, this is not good. There are some things that you have to have just on quick recall and be able to do. You should not be looking up the formula to calculate the expected value. But in terms of, what is the actual probability density function? Well, I can access the web so quickly that it's really not a big deal if I forget some of this. This is why we have a lot more open book exams now, is you're going to have access to the information. Let's give you some challenging problems to think about. And now a lot of it's going to be gathering data and then trying to figure out what does the data indicate? What does the data suggest? And so how do you attack a new problem? How do you see connections? So the big thing is to ask questions. Always, always, always ask questions. Look at what you have and try to ask, is there a way to generalize? Is there a reason why this is true? Is there a miracle? Can I find out what that miracle is? And as I said a moment ago, gather data, observe what's going on in the world, write a computer program, simulate things. I like to use games to try to get people excited about mathematics. And so we will use a game later today. So this is joint work. Oops, let me see. It seems like it's missing on the bottom of the page. There we go. This is joint work with my kids from when they were younger. And it eventually led to a paper that was jointly written with 2 of my probability students. And so it began when, I gotta be careful because this is being recorded, my wife had just started teaching at UMass Amherst, and the kids were in daycare there. They did not really separate by ages. So 2 years, 9 months to 5 years were all in one classroom. And anybody who has worked with young kids understands developmentally, there's a big difference. They were not always age-appropriate toys. And at one point, the head teacher in the room told me that she had listened to my request for more age-appropriate toys for my son, who was on the older side of 4, and she showed me a 15-piece jigsaw puzzle. At this point, I started bringing my kids out of daycare a little bit earlier each day and just doing various things. And so one day my son asked me, if you're born on the same day, do you die on the same day? This is a really good way to ask a question about randomness. I'm being very careful. One possibility is my wife is an identical twin. Look, mommy's still alive. Okay, no, this would not work for a variety of reasons, right? But it is one way as a mathematician to show, look, not everybody born on the same day dies on the same day. Can we have a more socially acceptable way of talking about randomness? So I created the Eminem Game. And this is one of the earliest known photographs of the Eminem Game. It turns out when you're very young, it actually matters which color M&Ms you get. So you can see the Kayla, she really wanted the blue M&Ms. Kim and I went for alternating patterns. And so the way the game works is everybody starts off with the same number of M&Ms. We did 5. And you toss a fair coin at the same time as everyone else. And if it comes up heads, you eat an M&M. If it comes up tails, you don't. And when you are out of M&Ms, you're dead. When I explained this game at a children's party to one of my son's friends' grandmothers, she actually writes children's stories. And she wanted to use a modification of this, but did not really like the idea of people dying. So, well, no, that's actually fundamental to the game. We're not going to soften this up. This was inspired by. So what kind of questions might you ask about this game? Good, so what's the average amount of turns before, how many days before either someone is dead or everyone is dead? Good, what else? There's no wrong questions, it's what could you ask? So you could do that, that puts you on the, allegedly there's not supposed to be a difference in taste. What mathematical questions can you ask? So it could be how long until the other people die? What are the odds of winning? Or what are the odds of there being a tie? So everybody tosses at the same time. So 1, 2, 3 toss. And so, the questions I wrote down is how likely is the tie as a function of the number of M&Ms? It could also be as a function of the number of players. How long until one dies? You could generalize, what if you have more people? What if you have a biased coin? What if your probability of a head is now only 20%? How does that change the probability of a tie? So let's gather some data. So I did extensive simulations and I recorded the various probabilities. And so I'm having 2 people play with exactly K M&Ms. And so with 1 M&M, there's a 33% chance of a tie. With 2 M&Ms, it was a 19%. With 4 M&Ms, it was down to 10%. When you look at this, can you give me immediately the functional form of this? No. What if I give you a little bit more data? Looks like some kind of exponential decay. Not entirely sure what the base is, but maybe I could try to estimate it. Do you want to predict, does it go all the way down to 0 eventually, or do you think it stabilizes? So what do you think? Do you think it stabilizes, or do you think it goes to 0? So we have 1 vote for 0. Anything for stabilizing? Stabilizing. So we have 2 stabilizing. And so the problem is exponential decay is very, very slow. So the log of 10 to the 10 is 10 log 10. Log 10 is about 2.3, so we're talking about 23. That is not that much. But 10 to the 10 is huge. And so the problem is, if it is going to 0, it's going to 0 at such a small rate, it's going to be hard to tell. If this is 5%, what would you estimate this at around? Maybe 2.5%? What would you estimate the probability would be at around 220 years? If it's stabilizing, is it going to still be around 2.5%, or is it going to be much less? Any rough guesses? Around what? 1.5%. So let's see. So again, we're going to gather some data. And so it's how to predict what comes next. So I don't show it yet. So what I do to try to get some better predictions is I do a log-log plot first. What does this look like? Yeah, it looks like a line. And then, fortunately, somebody left some paper here. Great. I can put this up here. Yeah, that looks pretty much like a line, and try to find the best fit line. How many of you have seen how to find the best fit lines? Okay. So we're going to do that on Monday. We're going to discuss the mathematics of how to find the best fit lines. This is linear regression, one of the most important tools we have. And I'll talk about some real world applications I've done with linear regression. We might have to have some equipment malfunction. So if we try to do the best fit line, we get negative 1.42 blah minus 0.545 log number of M&Ms, or about 0.2412 divided by k to the 0.5456. And again, there's no way you're going to look at this and see those numbers. We can see how good of a job we do. So we estimate when there are 220 M&Ms that the probability of a tie is about 1.27%. The actual answer is about 1.37%. First of all, this is actually within the ballpark of your 1.5, which was not bad doing it from your seat. Do you think this is a decent estimate? So percentage-wise, it's a big difference. If you look at the amount that we're off by 0.00, yeah, 27, something like that. We're not off by that much. We're going from, we're off by less than 1.001. But on an absolute scale, 1.37 versus 1.27, it's a sizable percentage error. How good of a line do you think this is? Say that again loudly. It gets better as you go farther down. That maybe in the beginning, the pattern hasn't really sunk in yet, and we shouldn't pay too much heed to those first few points. So the small values can distort and mislead. So when you're looking at data, throw away sometimes certain data. Says, look, I'm trying to go for the limiting behavior. Small values, that's too soon maybe for Stirling's formula, other things to really kick in. Let me just look at like the last 50 or 60. So now here's my best fit straight line for the last 60 data points. If you look really closely, you might actually see that there is a red line going right through the blue dots. That line looks much better than the line we had going through everything. And now, we have a slightly different prediction. Now it's 0.2054 k to the 0.505 versus 0.241 k to the 0.546. And when we do our prediction, we get 0.01344, and the actual answer is 0.01347. So we're off by 0.00003. And percentage-wise, that's extremely small. This is incredible. This illustrates the power of prediction. Oh, it seems like you've okay. So again, this is the power of logarithms. This is the power of regression. This is the ability to make incredibly accurate estimates from small amounts of data, but a lot of it is trying to figure out which data to look at. And again, this is not a proof. This is just saying, this is something to look at. This is my prediction. Let's see if we can prove this. All right. So the next part we've seen before, so I'm going to go through this pretty quickly. One of the reasons I like to do this is a chance to review some of the material from earlier in the semester and just really drive home how valuable this is. So we've seen the hoops game before. Again, I'm old. I like Bird and Johnson. And so first one to make a basket wins. Bird always gets it with probability P, Magic with probability Q. X is the probability that Bird wins. And then the solution typically involves just writing things down as a geometric series. What's the probability Bird wins on a given number of shots? And so since we've done this a few times, I'll just quickly write down what it is. So the Bird wins on the nth shot. He and Magic have n-1 failures, and then Bird succeeds. If we let R be the product of them both missing, then we get the probability that someone wins, X, is just this nice geometric sum, P1 plus R squared, and so on. But we can also solve this without resorting to the geometric series formula. And the reason is we have a memoryless process. And so once Bird shoots, well, if he gets the basket, that's great, he wins with probability P. If he misses and then Magic misses and Bird has the ball, it's just like he's starting all over again. And so by definition, the probability Bird wins is X. And so we now have a finite equation. We have a finite sum. This is very different than the infinite geometric sum. Whenever you have an infinity in mathematics, this is a danger moment. We don't have that danger moment now. We have a finite sum. We can solve for X trivially. And if we solve for X, we just get X is equal to P over 1 minus R. And so this is the probability that Bird wins. And then as a nice consequence, we get that the geometric series, if R is less than 1, is just 1 over 1 minus R. We've technically only proven this when R is a non-negative number. I think if R equals 0, it's okay. You can extend this argument to R being negative. So for extra credit, how would you get negative R just by knowing what's true for positive R? I don't know if you can make this work for complex values of R, but negative R, there's a nice trick that allows you to get negative R from knowing this. So I'll make that extra credit. All right, so the power perspective, this is a memoryless process. We converted an infinite sum to a finite sum. The depth of a problem is not always what you might expect. We thought, oh my God, we have to handle this infinite sum. We have all these different cases. No, there's only 2 cases to look at. So just because something looks hard initially doesn't mean it's actually hard. If you continue in mathematics and you get into cryptography, this is the entire subject. You're trying to come up with an encryption scheme that not just looks hard, but actually is hard. And sometimes people find clever ways to break into things. All right, so I want to now talk a little bit about the Eminem game. I will describe later why this formula works, but this is the formula that describes the probability of a tie with 2 people, fair coins, and everybody starts with K M&Ms. So it's an infinite sum involving the product of binomial coefficients. Right? Is anybody excited about such an infinite sum? Right? Let's try to make it finite. Right? Now, it turns out infinite sums like this have been studied. Has anybody here heard of hypergeometric functions? Right. So they arise in mathematical physics. This turns out to be a special coefficient or a special value. I will put in quotes that it simplifies to 4 to the negative k times the hypergeometric function 2f1 at the point kk1 1/4. Right. So if you want, if you're interested in mathematical physics, just look up hypergeometric functions. They are solutions to very important differential equations. Special cases correspond to special functions that you've seen before. I can just give it a name like this, but what does this really mean? Let's try to find a better way. So where did the formula come from? Well, on each turn, 1 to 4 things happen. They both eat an M&M. Cam eats and Kayla doesn't. Kayla eats and Cam doesn't, or neither eats. And the probability of each one is 1/4. So what would it mean for the game to take exactly n tosses and end in a tie? It means going into the nth toss, each person has eaten exactly k-1 M&Ms, and the final toss has to be heads. So that's where the factor of 1/2 and 1/2 comes from, that they both toss a head on the nth toss. Now, for them to have exactly 1 head M&M left at the time, that means in the first n-1 tosses, Cam got k-1 heads, and similarly, Kayla got n-1 of her, got k-1 heads in her first n-1. And of course, since it's a fair coin, it's just the probability of 1/2 for each. So this is the way to derive this formula. Okay. But in the hoops game, we learned about memoryless processes that reduced an infinite to a finite. Does anybody see how we can turn this into a finite game? Good, so they both toss tails, it starts over. So how many outcomes are there really after each toss? 3, right? So we can really assume that there's only 3 possibilities, because if neither eats, just pretend it didn't happen. It's been a decade, wow. And Kayla still remembers the time we played and she got 5 consecutive heads and got to eat all of her M&Ms quickly. It's amazing what stays with you when you're 2. Okay, so now the probability of each event is 1/3. And so I'm not going to go through and derive this, but again, to end in a tie, they have to have their final toss both being heads, and it has to be each one of them has exactly 1 head left. And so if you look at what happens before, I have to have some number of tosses that are heads, and for each of those, they both lose 1. And then there has to be some number of tosses that are going in each way. And so I'll leave this as an exercise to prove that something like this is correct. But all I really care about now is that you agree that there's some finite version for this. Okay. Let's try to figure out in a little bit better way where this is coming from. So why am I choosing C and K to represent the number of M&Ms? Yeah, it's their names. You always want notation that's good that you can quickly look at and see what's going on. You have C for Cameron, K for Kayla. Why was Cameron listed first? Older, that's one possibility. I did alphabetical order. But again, the main reason for stuff like this is you want to make sure you don't omit cases. Sometimes earlier in the semester when we were looking at how many ways can you order things, you want to go through in a very nice logical way. If you've done any logic theory tables, when you have like P and Q implies not P or not Q, if and only, something like that, you have your table for possible truth values and you go through all true and then all false, and then half true, half false, half true, half false, quarter true, quarter, so that you always make sure you don't miss anything. All right, so each of the following happens 1/3 of the time. CK goes to C minus 1, K minus 1, or to C minus 1, K, or to CK minus 1. And so let's write this graphically. So again, the goal today is to show you there are so many different ways of approaching a problem. We're going to keep getting the same answer. And so here I start at the 0.44. Why not 5.5? Well, you can see how long it took to draw this picture. I didn't really want to draw anything further. If I want to end in a tie, they have to get to the 0.00. The only way they can get to the 0.00 is they have to be 0.11, and they both have to toss heads. So at every moment in time, you can have either exactly one person eat an M&M, or both eat an M&M. And that's why there's always 3 arrows going out of these points. And so if I start off with 100% probability at 4.4, I can look and see how the probability flows as I go down the tree. I would not want to draw this tree for 1,000 M&Ms, but to do something simple like 4, I can easily do that on a piece of paper. So let's just go through this slowly. So I start off with 100% probability at 4.4, and then it splits to 1/3, 1/3, 1/3 at 4.3, 3.3, 3.4. Right? Now for each of these, I have to see how the probability splits. What do I have to be careful about with 4.3? Where could it possibly move? It could also move to 3.3. So what I'm going to do first is I'm going to see how 4.3 and 3.4 split, and it's going to reinforce some of the probability of 3.3, and then I'll see how 3.3 splits. So when I do that, again, some of the probability from 4.3 and 3.4 goes to 3.3, and then once I have that, then that all comes down. And so you start to see a little bit of an asymmetry: 1/9, 8/27, 5/27, 8/27, 1/9. Okay, and now I just lather, rinse, repeat. Shampoo mathematics. I just keep doing this. With the 4.2, I could also go to the 3.2. The 3.2 can go to the 2.2. So I would first figure out how the probability splits from here, and then just keep going down. And so just doing it very carefully, just doing the 4.2 first reinforces a little bit of some of the others. And again, at this point, it's just just keep slowly doing it. Now I do the 3.2 and the 2.3, and then I do the 2.2. And so again, I can just keep track of the probabilities. It's not so bad. Now it's easy. I only care about the probability that's coming inward because I've got to get to the 0.11. Any probability that comes below is not going to end in a tie. So I just have to see, well, that's just 1/3 of its probability just marches to the right or to the left, depending on where I am. And I just keep going down like this until eventually I get to 245 out of 729. And so that is the probability, or about 11%. So with 2 people, there's about an 11% chance of a tie. All right. We've talked a little bit about Fibonacci numbers from generating functions. We've talked about Benet's formula. If there's time at the end of the class, I'll just quickly warp through those slides just for completeness of lecture. We talked about how you can get a closed form solution to the recurrence relation. Well, we really have a recurrence relation for the Eminem game. It's just a more complicated one. The Fibonacci's was a recurrence relation with 1 index. So how many people had seen recurrence relations with 1 index before this class? Had no one seen like Fibonacci numbers? Right, that's a recurrence relation with 1 index. This is a recurrence relation with 2 indices. XCK goes to 1/3 XC minus 1 K minus 1 plus 1/3 XC minus 1 K plus 1/3 XC K minus 1. So XCK is going to be the probability we end up with a tie, given that Cameron has C M&Ms and Kayla has K M&Ms. I will define if I start off with 0 M&Ms for each. I'm going to just declare that as a tie so that there's no fighting as to who won. And if C is greater than 0 or K is greater than 0, XC0, X0K is going to be 0 because it can't be a tie if one of them is out of M&Ms and the other still has it. So I have a two-dimensional recurrence relation. There are ways to solve two-dimensional recurrence relations, but again, we can just do it by brute force. So notice I said that there was the simple recurrence relation. We noticed that there was a memoryless process, and that led us to this. What if we weren't clever enough to see that there was a memoryless process? Well, we would have then written down a little bit longer because there would have been 4 possibilities. And so instead of 1/3, we would have 1/4. So we'd have this extra term 1/4 XCK. Oh, but what can we do to both sides? Yeah, subtract. And when we subtract, we would then get 3/4 XCK. So we divide by 4/3. It's really annoying that it's cutting off the very bottom of the screen, but you can probably extrapolate that those figures are 3s. And there's our simpler recurrence relation. So if you hadn't noticed this from the beginning, when you start to do the algebra, it might even suggest to you that there is a memoryless process lurking in the background. All right, how do we solve this? Well, we now have this recurrence relation. What you do is you start off with small values and you work your way up, you build. And so we know x00 is 1. And so now if we want to calculate what x11 is, well, we know x10 and x01 are both 0 because somebody has an M&M and the other one is out. And so x11 by the recurrence relation, 1/3 x00 plus 1/3 x01 plus 1/3 x10, and we get 1/3. So now we know x11. If we want to calculate x21 and x22, well, we know x20 and x02 are both 0. So now we can calculate x21 and x12. And now that we have those, now we can calculate x22. You can see that this would not be that bad to do for a computer program or a spreadsheet. There is a formula you can try to develop. But again, this is not that bad to code if you solve them in the right order. You don't solve for x22 first, you solve for x21 and x12. And before you get those, you get the x11. Okay. So again, we want to always try to find easier problems and build intuitions. So another way to look at this is we're walking in some sense from 0, 0 to kk, and the only steps we can take are the steps 1, 0, 0, 1, and 1, 1. And we want to hit kk before we get to either the top or the right side. How many of you have heard of Catalan numbers, where you're walking and you always stay below the diagonal? Okay. This is something that another way of phrasing this is you have a bunch of left and right parentheses, and you want to put the parentheses down in such a way that as you read from left to right, you never read more right parentheses than left. Because if you're doing a valid parenthicalization of something, you should never have more right parentheses read than left parentheses. And so how many ways can you do this? This is the Catalan numbers. They turn out to occur throughout all of mathematics. It's absolutely wonderful how many places they come. And so this is a generalization of the Catalan numbers. We just have a little bit more movement. For the Catalan numbers, you can't move 1, 1. You can only move left and right and up. And so for the Catalan numbers, it's the number of ways to walk from 0, 0 to kk and to always stay below the main diagonal. And it turns out huge volume of literature on this. There is a recurrence relation for this, but it's not of constant depth. The number of terms you need grows with n. And in fact, it involves products of terms. But absolutely beautiful mathematics here. Let's skip this. And so what I'm going to do is I'm going to just report on the results. So I have done the calculations, and here are the values when k goes 1, 2, 3, all the way up to 8, and the probability of a tie. You are now detectives. When you look at these numbers, these probabilities, do these numbers look like they have any interesting properties? Do you notice anything? Yes. They're all powers of 3. Is it the same power of 3 going from one to the next? Why not?
Well, I mean, these.
So going from the first to the second, we multiply. From the first to the second, we multiply the denominator by 9, right? For the next one, we multiply the denominator by 3. And then what do we multiply it by? So let's see. I really like 27 because we end with a 7, right? 27 is roughly 30. Make 81 80. 80 times 30 is 2400. So I really like 27, given that this is about 2200. Yep, so it's 27. So so we multiplied first by 2 powers, then by 1 power, then by 3 powers. But there might be a reason why it's a little bit misleading to look at what we multiply the denominators by. Yeah, the numerators might have powers of 3, and someone might have thought that they were being helpful and simplified and put things in lowest form. No, that's actually not helpful. How many of you have ever heard of the OEIS, the Online Encyclopedia of Integer Sequences? Wonderful website. I once gave a talk when I was a postdoc at Brown on how to use this website to prove mathematics. And in fact, I was just emailing the creator of the website, Neil Sloan, yesterday with some results and a paper that I had written recently with some students at Small last year. Turns out the denominators look like 3 to the 2k minus 1. And if we multiply by that and clear denominators, we now get a sequence of integer numbers, 1, 5, 33, 245, 19, 21, and so on. Does anybody recognize these numbers? I don't. But you feed them into the encyclopedia. So you go to oeis.org, put that in, and our sequence exists. And it spits out, it's the coefficients of 1 divided by the square root of 1 minus 10x plus 9x squared. Also, it's the central coefficient of the following. And then it lists a bunch of contents, references, tables, formulas for them. So this is not a proof, but all of a sudden, remember, if you're doing a proof by induction, if you know what you're trying to prove, boy, that makes things easier. And so the OEIS can help us and can inspire us in terms of trying to figure out what we want to prove. All right, so just a couple of quick takeaways. The value of asking questions. Related to this, I guess, is getting paid to do the same thing from multiple sources. So this was inspired by doing something to amuse my kids. But from this, I now have lectures that I've given to math teacher conferences, to undergraduate math clubs, to probability class, plus a publication with students from probability. There are often many ways to look at a problem. Different perspectives have different value. We looked at this as a graph problem. We looked at this as a recurrence problem. We looked at it as an infinite sum and related to hypergeometric functions. There's lots of ways of looking at it. A lot of advanced combinatorics comes down to you want to solve a problem which is really hard, so you show it's equivalent to another problem which you can do. And the whole point is you have 2 different ways of computing something. And as long as you can do one of them, then you're okay. We also saw the power of the memoryless process idea. This is very similar to the bring it over method we did for integration. Wonderful, wonderful idea in mathematics. The more times I can emphasize this, the better. It allowed us to reduce an infinite problem to a finite problem. Another thing to mention is just looking at the data the right way. This is a joint math stats class. This is not a pure math theory class. We want to talk about real world data, and we will talk about that next time, in particular about the Mount Greylock Regional School District, which has to do a linear regression each year. We even talked about it at the Finance Committee meeting yesterday. It's time to do the linear regression again. I love that we have to talk about this each year. And I've said this many times, if all you have is a hammer, pretty soon every problem looks like a nail. Whenever you see a product, what should you be thinking of? Logarithms. Always be thinking of logarithms. And this is one of the reasons why I wanted to spend a couple of minutes today to just give a brief lecture on logarithms. It's not often that we have a chance to go back and fill in gaps from previous years. Logarithms is a crucial gap. Too many times people can manipulate mathematics without understanding what you're manipulating. What is the derivative of x times the natural log of 5? with respect to x. Okay, and how did you calculate that? What rule did you use to say the derivative of x times the natural log of 5 is the natural log of 5? Power rule. Power rule? Not power rule. What rule? I'll eventually prove everybody is named the same, so then you can say all the differentiation rules are the same. You did a limit in your head. This is like the great joke of a bug is flying back and forth between two trains that are speeding towards each other. The trains are traveling at 75 miles per hour each. They start off 150 miles away. How far does the bug fly before it's smashed? And so what's the answer? Trains start 150 miles apart. Each one is traveling at 75 miles per hour. How far does the bug travel? And the bug is flying at 200 miles per hour. So the bug flies from one, I'm sorry?
200 miles.
Nope. Oh yeah, yes, 200 miles. Why?
Because it's flying right now.
It's flying, it's 1 hour before the two trains hit, so the bug travels. And so the joke is one of the famous mathematicians was once given this problem, and he immediately said 200 miles. And he said, that's, this is why you're so great. Most people, don't notice that you just have to see how long the bug is traveling and they sum the infinite series. His response was, I did sum the infinite series. You want to look at the right way of looking at things. If I have a hammer, I try to convert every problem to something where I can use my techniques. I can use what I'm good at. All right, so just very quickly, just to put the slides up there, these are the slides we've seen before on how we use generating functions to get Benet's formula. There's other ways to get to Benet's formula. This is building up a function by saying, well, let's take the Fibonacci relationship. Fn plus 1 is Fn plus Fn minus 1. We'll put in that F0 is 0, F1 is 1. We build a function. We play some games shifting the summations. If you take a class in differential equations, when you look at series expansions to solve problems, this is huge there. We get the function, g of x, the generating function, is x over 1 minus x squared. We don't want to expand it directly because x and x squared, if we let that be r, it's not homogeneous. The polynomials have different degrees. It becomes a nightmare when you expand. So we use partial fractions. There was a reason we learned partial fractions. It's not just, again, because teachers hate us and want to give us, painful problems. Partial fractions make problems like this very easy. And now when I factor it like this, I can expand each one of them very easily and then just collect the x to the n and then just match coefficients. All right, so this finishes the lecture on the Eminem game. What I really want you to get from this is using the techniques we've done to attack real problems and trying to find what is the right way to look at the problems so you can get a sense of what is the answer. And when we take logarithms, all of a sudden, things become easier for us to see and pass. A lot of it is training. I have heard that there are studies that if you take a standard deck of cards and replace the suits, spades, hearts, diamonds, clubs with vegetables, that novices have trouble. Whereas expert card players, okay, so now I have carrots, cauliflower, broccoli, and asparagus. Not a big deal. They just quickly change. If you get used to something, it's often hard to look at it from a new perspective. But that's often the greatest chance to make real progress. Is can you step back and say, is there another way to look at this? The logarithm is one of the best ways to look at things in a different perspective. And this is a point that should have been emphasized earlier in your career. I am glad that we had a chance to do that today. All right, so this is a good place to stop.